So, in these set of lectures, I will give a brief introduction to thermal physics. So, essentially I will be talking about thermal physics. First thing will be heat and temperature. I will be doing heat and temperature. I will tell you what is heat and what is temperature. Secondly, kinetic theory of gas. Thirdly, thermodynamics. And fourth, thermal properties. Of matter. So, as we know, materials have properties, elasticity and other properties which are mechanical properties. Here I will be talking about thermal properties of matter, which means if I increase the temperature, how does a material respond to that change in temperature? That is what is reflected in the thermal properties of matter. Then what is kinetic theory? I will elaborate on that, and what is thermodynamics? I will also elaborate on that. Now, let me first ask the question, what is heat? So, first question which I am going to ask is, what is heat? Well, in physics we know everything we deal with has to do with energy. So, we talk about mechanical energy, which we learn at length in our mechanics course. These had two pieces. One is kinetic energy, which we talk about, and then for interacting systems, which we talk about also potential energy. If there is a force, a particle is subjected to a force, we can talk about a potential energy. So, heat is nothing but a form of energy, a form of energy. Okay? Well, how do I know it is a form of energy? We know that anything which is related to energy can be obtained from other forms of energy. So, what do we know? For example, if I have a rough surface, with a friction, and then I drive an object on this surface, I push it, then I know I generate heat. That means the mechanical energy is converted to heat energy. Okay? So, energy flows from one end to the other. We know heat energy goes from hotter to cooler bodies. This is how it propagates. So, it is the form of energy. And what is temperature? Temperature is a measure which dictates which direction heat flows. Okay? It always flows from higher to lower temperature. So, when I talk about temperature, I know that temperature should be measured with something called thermometer. Okay. We know of mercury thermometers in our day to day use, and we can think of various other kinds of thermometer, but here let us try to give some different description of temperature. Temperature in the sense of kinetic theory of gas, kinetic theory of gas, I can say temperature capital T. I will soon tell you what is capital T. Capital T is the temperature measured in some scale which I will call absolute scale of temperature. This I am going to define soon. So, kinetic theory of gas, there is a definition of temperature which says that T is proportional to average. This word is very, very important, this word average, okay. Average translational, that is also very, very important, and I will be talking about ideal gases mostly. It is a kinetic energy. So, it will be proportional to kinetic energy of the molecules, and that is a more well defined definition of temperature. You know, when we increase temperature, there is always vibration in the molecules. Molecules can go from solid to liquid and liquid to gaseous. In the process, they gain more and more energy because temperature comes, and average kinetic energy of the molecules keep on increasing. Okay? But now comes the question, if I define a temperature, I can define a thermometer, and we all know from our basic 9th 10th standard education that thermometer is a scale where we always talk about ice point, which is the lowest, ice point which is the lowest, and steam point, let us say steam point which is the highest scale, which we know 0 degree and 100 degree Celsius of water. These can help me in calibrating my thermometer, and this sets the scale. So, we can measure anything with respect to these two temperatures. In our Celsius scale, one is 0 degree and other is 100 degree Celsius. Now, coming back to the point, what do I mean by average? Why I am calling it is a average distribution, average. Well, firstly, I have written down already two things. One is kinetic theory of gas and other is thermodynamics of gas. Now, what do I mean by average? Okay. Firstly, this is first time I will be dealing with a huge number of particles, huge number of particles. What I mean? That I will be dealing with a system of particles with 10 to the power 23 molecules, let us say, which is typically the Avogadro number. We all know a huge number of particles numbering 10 to the power 23. What we have learnt in our mechanics? Each molecule described by Newton's laws, which is mass of the molecule, let us say m, and I can write d2 x dt2, the force acting on the molecule. So, this is my Newton's law. Now, you see this is a vector equation. A position vector of the particle has 3 components. Now, I will be totaling these type number of equations, which is impossible for me to handle with. I cannot handle with 10 to the power 23 particles. I cannot handle with this many second order differential equations. As you know, we cannot solve this problem by any means, even using the most advanced computer what we have today. So, we must have an average description. Here comes the advantage and also the difference between kinetic theory. So, I need an average description, and here comes absolutely the necessity of doing kinetic theory and thermodynamics. Okay. So, let me first ask the question, what is kinetic theory and what is thermodynamics? Okay. Then I will go to the details of other things I will talk about. Firstly, kinetic theory. Here I will talk about distributions. Okay. I will look at distribution. I will look at gas molecules and probe the distribution, for example, of their velocities or speed. So, though I talk about a molecule here, I am not really interested in an individual molecule and its behavior. Rather, I will be interested in the distribution of their velocities. From that, I can talk about average of velocity, some average of velocity, which will give me some average of kinetic energy, okay, and from that I will try to find out what is the temperature. I will relate it to the temperature, I will relate it to the pressure and volume of the container. So, here I will be talking about molecular level, but please note I talk in terms of molecular levels in an average sense. So, I need a distribution of velocity, and that distribution of velocity will give me average properties which will be related to kinetic energy. For example, I will be talking about average kinetic energy. These average kinetic energy will be later related to temperature, pressure and volume. Okay? This is the approach of kinetic theory. What is the approach of thermodynamics then? Well, in thermodynamics, we really do not care about individual molecules. Okay? I do not care about molecules, their velocity distribution, nothing. So, kinetic theory, if I use more formal language, it is a microscopic theory. Microscopic theory. At the microscopic level, I am trying to see what is happening to the molecules. Thermodynamics, in some sense, more formal language, is a coarse grained description. Coarse grained description. What do I mean by coarse graining? Coarse graining means I do not look at molecular level, rather I look at macroscopic levels. Well, I look at macroscopic levels. Okay? And the macroscopic level, let me erase this part. In the macroscopic level, I will just consider the measurable quantities. For example, measurable quantities. All the physics, all the equations I am going to write will involve only the measurable quantities, namely pressure, volume, temperature and so on. You see, pressure, volume, temperature, these are the quantities we measure in experiments, but there is a difference. volume is a quantity which is subtly different from pressure and temperature, which I am going to say later. There are quantities of two types, one is called extensive quantities and other called intensive quantity. I just throw the nomenclature at the moment. Pressure and temperature are intensive variables. So, they are intensive variables, whereas volume is an extensive variable. Okay. Now, do these two approaches which I mentioned here, do they lead to different set of results? No. When I talk about these two approaches, maybe they are two different approaches, but if I am in equilibrium, whatever I will talk about is related to equilibrium. Okay? And in equilibrium, whatever I measure, okay, in physics it is important that whatever we measure should be independent of the theory I construct. So, therefore, in equilibrium results arrived from kinetic theory or results arrived from thermodynamics, they should be same, identical result. Okay. Now, before I proceed further, I should tell you what is equilibrium. I will give a very informal definition in the beginning, that equilibrium means nothing depends on time. Okay? Nothing depends on time. I measure pressure, I measure temperature, for example, with a thermometer. Maybe it is my just medical thermometer, clinical thermometer, whatever I measure, measurable quantities, nothing depends on time. So, you can, for example, you can take a liquid in a container and stir it, wait sufficiently long, okay. Now, everything settled down and you say that system has reached an equilibrium configuration, which means no longer my measurable quantities depend on time. So, in equilibrium if I study, kinetic theory will show a different approach to equilibrium, maybe thermodynamics will give you another approach to equilibrium, but I will be constantly talking about equilibrium, and in equilibrium whichever approach I take, kinetic theory or thermodynamics, my ideal gas equation PV is equal to nRT, if you like, PV is equal to nRT, whatever n number of moles, okay, it does not change. So, this is very, very important, that equilibrium results do not depend upon whatever approach I am going to take. Now, since I have come to ideal gas, now question is, what is an ideal gas? Okay. First question is, what is an ideal gas? This is something with which we have to spend plenty of time, and then idea should be clear. Name itself suggests it is not real gas, not real gas, okay, because you soon see the assumptions and it will be clear to you why I am saying that it is not real. First, I will assume there is a point particle. So, all the ideal gases I will assume to be point particles. So, it is very, very tiny, or rather more formally one can say that I will assume that size of the particle is very, very small compared to the intermolecular distance. Okay. So, that is what I mean by point particle, that interparticle distance is very large in compared to the size of the molecule, if you like. But remember, this is an approximation, ideal gas approximation. Second thing is, I will assume there is no interaction. This is not true. We know that whenever we have molecules atoms, they are occupying a container, there must be an electrostatic force, and typical interaction between two molecules, if you like, it is attractive when they are far apart and they are repulsive when these two molecules approach each other. So, you see, I cannot assume that they are not at all interacting with each other. Okay? So, this is also an approximation that they have no interaction and the energy is then entirely kinetic, entirely kinetic. Okay? Now, fourth condition, this energy is entirely kinetic and they have collisions. Okay? Collisions, but these are all elastic collisions. This is very, very important. These are elastic collisions, no interaction, and collisions which are completely elastic in nature. So, no energy is dissipated, energy is entirely conserved. Now, question is that whether I can have this type of ideal gas in nature. Well, point is that I cannot get an ideal gas in nature, because these two conditions is never satisfied. But is this a situation? Now, question I am going to pose to you, that is there a situation when I can approximate a real gas as an ideal gas? Well, often you will find the answer in the books, but I will try to explain to you why in some limiting situation, okay, ideal gas can be approximated, ideal gas can be approximated as a limiting situation. Okay. Now, this can be very easily thought in terms of comparing different length scales of the problem. Well, I am using a jargon, length scale, you will soon see what do I mean by length scales. Okay. Firstly, interatomic distance, I told you, or intermolecular distance in a gas, average intermolecular distance, that I can say is a length scale of the problem. Okay. That easily can be found, it is related to density. If I have a container of volume V and in that volume I put n molecules, so I know V by n, typically this to the power is typically on an average, this is my intermolecular distance, and now I should be able to compare this distance with other length scales of the problem. Let me bring in something which you will learn later or already you know, that if I have a particle of momenta p, okay, roughly momenta p, I know from wave particle duality picture that there is a lambda associated with this, which h over p. Okay. Now, roughly in a very hand waving sense, let us assume that the average kinetic energy of a molecule, which I know, is of the order of kT, then you know P is of the order of root over 2 mkt. So, you see there is a wavelength or there is a length scale associated with this is which is 2 mkt. Okay. Now, look at these two length scales. This, if you do not know, you have to just look for de Broglie wavelength. What is de Broglie wavelength? And what I have said that there is a length h over p, and typically kinetic theory tells us, which I will elaborate on later, that p square over 2m is of the order of kT. So, p is of the order of root over 2m kT. So, this is the other length in the problem. So, I remind you two lengths, one is A, other is lambda. These two are to be compared. If A is much greater than lambda, let us say, somehow or the other A is much greater than lambda, all I can say particles interatomic distance or intermolecular distance, which is an important role, okay, is very high in compared to whatever the de Broglie length scale. This de Broglie wavelength tells you that particles are interacting with each other, maybe those interaction lengths are interactions may be of quantum mechanical nature. Let us not go into that. I am just constructing two length scales in this. One is de Broglie wavelength, which is given by h over root over 2 m kT, and other is A, which is interatomic distance. Now, you see the question I have, I need to have A much greater than lambda. How do you achieve that? You can achieve that in two ways. Firstly, increase the temperature. If you keep on increasing the temperature, very high temperature, you see your lambda becomes smaller and smaller. This quantity out here becomes smaller and smaller. Okay? If this quantity becomes smaller, this is automatically satisfied. A is much greater than lambda. You can say I am just having some isolated particles who do not interact with each other, and this is a limiting situation where ideal gas condition could be valid. Now, I leave it for you to think about it, that V by n, okay, you can look at the V by n quantity. This is inverse of density, because what is density? Density typically given by n over V. So, if I make n by V is my density. If density is lower and lower, A is automatically increasing. So, once again I can say A is much greater than lambda. If you do not like the concept of lambda, you just like how I can make A comparably large, very large in compared to the other length scales of the problem. First, increase the temperature or reduce the density. That is why in books you often see this statement that ideal gas approximation, ideal gas is a good approximation when T is high and density is low. Okay? This is the region where we can talk about ideal gas systems. So, I told you what is an ideal gas. Ideal gas is a limiting situation of a real gas if I talk about very high temperature gas and low density gas. And secondly, we all know the following things for ideal gas. For example, keep T constant, temperature constant, PV is equal to a constant. These we know famous as Boyles Law. Then if I constitute or have a given substance or given quantity of gas, I can write V is proportional to temperature, which is known as Charles' law, and then this is Boyle's law, this is Charles' law, and all together taken together for any substance, okay, or any amount of gas, I can have this equation PV is equal to nRT. R is the ideal gas constant, T is temperature, and N is the number of moles of the sample I do have. Okay. So, now this also helps us in defining the absolute scale of temperature. If you keep V constant, let us keep V constant, P is proportional to absolute temperature, and we all know if I approach T is equal to 0, or in Celsius scale, if I call it in Celsius scale, roughly minus 273 degrees Celsius, this is how my absolute temperature is. For example, absolute temperature 0 is my Celsius scale temperature minus 273 degrees Celsius, and then if I have 10, which means minus 263 degree of Celsius, and if this is absolute 0, that means I have reached in the Celsius scale minus 273 degrees Celsius, I will know that pressure of an ideal gas will go to 0. So, if I take a very high temperature or whatever you like, a very low density gas, so that it is roughly an ideal gas, if I plot P as a function of T at T is equal to 0, if we could reach T is equal to 0, this is very, very important, we cannot reach T is equal to 0, then pressure would be equal to 0 if I keep volume fixed. We know this is unphysical, T is equal to 0 is unattainable. But why do you need T absolute scale of temperature given in terms of these ideal gas equations? Because of this fact that it is universal. I am not using mercury, I am not using any other particular substance, rather I am working on something which is universal, does not depend on the material I put in the thermometer. So, I have a scale which is universal and which is independent of scale I am choosing. Okay. Secondly, it is always positive temperature. Now, you may ask me question, can I have negative absolute temperature? Well, that is not an equilibrium situation. In some books you will find they mention, very advanced book, mention negative absolute temperature, but remember here we are dealing only with absolute temperature which is equilibrium situation. In equilibrium situation it is always positive. Okay. Having this preamble and assume that we know bit of absolute scale of temperature, now let me proceed to what I know as kinetic theory of gas. Okay. So, kinetic theory of gas, definitely as I mentioned to you before, it is a microscopic description, okay, but in an average sense. I will explain to you what does it mean that I talk about in an average sense. So, I wrote few minutes back what is called a distribution, and there is some distribution of velocities. So, I do not actually talk about an individual molecule, rather I talk about a distribution. Okay. So, average is important, again I repeat the term, I write the term average. Okay. So, what are the properties I will be talking about? Molecules are moving in all directions. This is the first assumption I will make, all directions. Okay. And second assumption, as I told you, point particles. I will absolutely ignore any size of the molecules, okay, which is an approximation, but it is good approximation as long as size is smaller than interatomic distance. Okay. Third, I will not assume any interaction, no electrostatic interaction between the molecules. I will not assume any interaction, only interaction I will talk about is collisions. So, these molecules are kept, gas molecules are kept in a container. There is a container in which these gas molecules are moving in all random directions, okay, and only they can exchange energy through collisions, collisions between two molecules, this molecule colliding with this molecule, or they can collide with the wall of the container. This is something very, very important. Wall of the container gives me the pressure which I measure. I told you, whatever approach I take the approach of thermodynamics or I take the approach of kinetic theory, I will always be ending up same equation of state, same measurable quantities which I get from either of the approach if the system which I am dealing with is in equilibrium. Okay? So, these are main assumptions. Secondly, I will consider classical motion, though when I talked about de Broglie wavelength, I brought in a little bit of quantum, because all of you know that in the microscopic world, in the world of electrons, if we talk about, the world is actually quantum mechanical. That is why to tell you, to give you an inkling about that, I mentioned a bit of de Broglie wavelength. That helped us also to tell us the role of temperature in defining an ideal gas. That temperature I can define for an ideal gas. If it is temperature very, very high, I can assume that it is typically an ideal gas. So, now I will make two assumptions more. I will completely talk about classical motion. So, all these molecules satisfy Newton's laws of motion, nothing more than that, Newton's laws of motion. Okay. So, these elastic collisions which I mentioned here, collisions, they are all elastic collisions. So, these elastic collisions are all dictated by the classical mechanics. The mechanics we have learned, conservation of energy momentum, that is what I am just going to use here, and in the form of Newton's laws of motion. Okay. So, classical mechanics is the subject on which we will build our this kinetic theory course. This is first. Second thing, it is homogeneous. That means I will assume density is uniform everywhere. I will assume that density wherever I have a container, if I am very much inside the container, wherever I am, the density is independent. This is same everywhere. If I take the same amount of volume, number of particles will on an average will be the same in this volume wherever I place it inside the container. This is homogeneity. Thirdly, which is very, very important, I have a 3-dimensional system. In a 3-dimensional system, I know if I talk about velocities, velocities will be having 3 components, Vx, Vy and Vz. I will consider complete isotropy. In today, if this is our first thing, first discussion hour, I am throwing some jargons which will be familiar to you as I proceed. Complete isotropy means that three directions, if you like, three directions Vx, Vy and Vz, they are identical. Okay? If I measure something in the x direction for velocity, okay, I will be having same for y and z. There is no way I can distinguish that this is in the Vx direction, this is Vy direction, this is Vz direction. Now, there will be a distribution of velocities which I will call velocity distribution. An important point I would like to make, that velocity distribution is same, and as I am talking about equilibrium, is independent of time. I told you my definition of equilibrium is nothing depends on time. So, it is same everywhere, like I said density same everywhere, the distribution is also same everywhere. Now, since I have been talking without explaining what do I mean by distribution and what is probabilistic about it, because I am talking about average. You know, if I have a dice, dice has 6 faces. So, I can play the dice, I can get 1/3, 1, 2, all with equal probability 1/6. Okay? So, you know, there is a probability of getting 6 out of 6 in one throw is 1/6, because these events are not correlated. 6% doing it, 6% can get 6 different results. This can be generalized to a continuous system. I mean, here when you talk about dice, you throw a dice, you can get one value out of 6 possible values. Now, question is, I have a continuous variable, okay, which is, you can think of, if I could construct a dice which had many faces, this probability of getting these things becomes smaller and smaller. If I have 50 faces, I can have 50 values, but if it is unbiased, it can fall on any side. Okay? You have to extend your imagination to see that if I have a 50 dice with 50 faces, so what do I have? It can go from 1 to 50. What is the value? We get 25th. It is still 1/50th. But you see, probability has become smaller, the possibilities had become larger. So, if I keep on increasing this, eventually things become continuous. 1/25th, 1/50th, first it was 1/6. Now, if dice somehow has 50 faces, it is 150. If I could construct a dice with 100 faces, okay, in real world we cannot imagine, because we are living in 3-dimensional world. Okay, if I could, then probability would have been 100th. So, if I increase the possibilities, you see the probability also goes down. Okay, it can take a continuous value. Let us take such a random variable x, okay, simple random variable x, which can take any value x, okay, from -infinity to +infinity. You may ask me that, well, what is the average value? I say this information that x goes from -infinity to +infinity is not sufficient to tell what is the average value. We need something. What is the probability of having it between x to x plus dx? That is very important. That is called the distribution. Okay? So, now I want to give you what is the meaning of distribution. Okay? Let us say I know px dx. Okay? What is the probability? Probability is px dx. It is the probability that x lies between x to x plus dx. So, you can think of, I am doing many experiments, which in the standard example I have given means I am throwing a dice. Okay? In the standard example I have given, which means throwing a dice. So, now I am asking many experiments, and I am asking the question, assuming now x is a continuous variable which can take any value from minus infinity to plus infinity, I am asking the question, what is the average value of x? And that is given in terms of this probability distribution. Let us take a very simple example. Let us say Px is of the form e to the power minus alpha x square. Okay? Well, and then there will be some constant which is called normalization constant, because you know Px dx minus infinity to plus infinity. Minus infinity to plus infinity you are integrating. What does it tell you? It simply tells you the total probability, and I know that total probability is 1. If you recall your dice problem, okay, then every probability is 1/6 of any face. I am getting a single throw, I am getting 1, okay, or 2, all with probability 1/6, but total probability you 1/6 times 6 is 1. This is all written in a mathematical language. Okay. So, this gives me a constant n. We can forget about this n for this time being. But what we have to remember, what is Px dx? Okay, if you plot this function, okay, this is called a typical Gaussian function which goes like this. Okay. Now, look at this function. You ask me what is the probability at x is equal to 0, that is given by this number n. What is the probability of getting x plus infinity? You can see it is exponentially small, it is actually 0. Alpha is something positive, let me tell you. Alpha is something positive, greater than 0. Okay. So, if alpha is greater than 0, x infinity value is 0, x negative infinity value is 0, I am plotting Px as a function of x. So, you can see x going to positive infinity or x going to negative infinity, these probabilities are basically 0. You can ask me, what is the probability it lies between x to x plus dx? If this is my small interval dx, this is the probability. Okay. What is the probability of x? Is this. Probability is x plus dx is this. This is my x axis. Probability of having anything x and x plus dx lies within this region. Now, you may ask me, what are you doing? Because it is after all thermodynamic course, why are you talking about this probability distributions? I am just trying to give you the feeling of average. Why do I need average? You have to understand, I have 10 to the power 23 particles at my disposal, and given 10 to the power 23 particles, I cannot write Newton's laws, I cannot solve them, I have to go to a probabilistic distribution. For that probabilistic distribution, I need to tell you a bit about probability. If you ask me what is x then, average value of x, now you cannot tell x is this. If you write like your dice experiment, if you are done, it can take any possible value from minus infinity to plus infinity, and you are asking what is the mean value. If I do is many times, okay, this will be given by integration x Px dx. So, you are not talking about a value of x now, please remember, you are not talking about a value of x, rather you are talking about an average value of x. Okay. This is a brief introduction to probability theory. Now, I will tell you how it is connected to, very brief introduction to probability theory. Now, I will tell you how it is connected to kinetic theory of gas. Kinetic theory of gas tells you that I told you that average sense things are to be dealt with, okay, in an average sense. So, this brings in the concept of Maxwell's velocity distribution. Okay. Maxwell's velocity distribution, I will just briefly mention what is Maxwell's velocity distribution. What I have at hand? I have at hand ideal gas molecules, molecules in a container, okay, which is a volume V, and these molecules are doing random motion. Velocity components are Vx, Vy, Vz. I told you they are independent of each other. Okay? This is far beyond your limit. So, I just want to mention few things. This can be argued. This is Maxwell's velocity distribution. So, if you have Vx, Vy, Vz, this can be shown Pvx, Pvy, Pvz, dVx, dVy, dVz. I read out this mathematical expression for you. Remember, container volume is V. These are the components of velocity. Let us say distribution of this velocity. If I track a single particle, what is the probability of that velocity of that particle lies between Vx plus dVx. Now, this is a deviation from mechanics. Mechanics, I give you a force, give you initial condition and ask you the question. Okay? I ask you the question, what is the velocity after a time t? You solve Newton's equation, you tell me the answer. Okay, given the initial condition, and if it is a solvable force, you can do that. But here I have already gotten rid of force. There is no force. Okay, there is no force in the problem. But what I am talking about is a probability distribution of velocities. Three components of velocities. This is the Pvx, dVx. It tells you what is the probability that velocity lies between Vx and Vx plus dVx. Okay? So, this is a probability distribution. This has a form which one can write as up to some constant A, Vx square, Vy square, Vz square. Okay? I am not telling you at the moment what is this constant A, but you can guess what should be its dimension, because you know from dimensional analysis, if I write something in the exponential, V already has some dimension. Okay? So, this A should be something that the whole quantity is dimensionless. Okay? I am not telling you what is this A, okay? But this should be such that the whole quantity as a whole is a dimensionless quantity, and there is also a speed distribution. Now, I do not care about the components, rather I ask the question, what is the probability that speed of the particle lies between V2 V plus dV. What is V? Speed. V is root over Vx square, Vy square, Vz square. That is my speed. Okay? Now, speed distribution, similar form Pv dV, or you can ask me how many particles are on an average having velocity nv whose speed lies between V2 V plus dV. I put another constant A, e to the power, let us say I call it B this time, bv square dV. I am not telling you what is A, what is B, but again B can be argued out, remembering that exponential minus bv square should be dimensionless. Okay? So, this is the distribution. This is far advanced, but I just wanted to tell you that what is average. We often see in books that the people talk about, I will talk about average over some distribution. Whenever there is a probability, there is a probability distribution, and if you ask me what is the average speed you can calculate taking the integral of this form here, given here. So, this is the average. So, we talk about average velocities, average kinetic energy. But let me ask you a question. Now, I have random motion of the particles, okay. I am inside a container, okay, and here I have two boundaries. Let us say this is my boundary 1 and this opposite face is my boundary 2. Now, if it goes randomly with equal probability with velocity Vx in the positive direction, equal velocity minus Vx, okay, in the negative direction. If this is my x axis, let us say this is my Vx axis if you like, it goes like this with Vx and comes back again with minus Vx. What do you expect to the average to be? I will tell this answer later. I just do not want to tell you, but it is obvious since particles are moving in the equal and opposite direction with equal probability, there is nothing that distinguishes plus Vx and minus Vx. If you look at this expression, it is given in terms of Vx square. So, there is a equal probability of having Vx and minus Vx because it is given in terms of Vx square, probability is given in terms of Vx square. So, average you would expect to be 0 and that is indeed the case. Okay. Now, we have next what I will do in the next set of lectures, I will put ideal gas in a container and try to form an equation state which is PV is equal to 1/3 Mn, let us say V square average. I will explain the meaning in the next class. This V square average is actually averaging in this sense. So, what I told you today that there are two approaches to study the thermal properties or equation of state of a gas or for that matter any system. One is kinetic theory approach where you go microscopic, other is thermodynamic approach. In equilibrium the results would be the similar. I have started with the kinetic theory approach. I have tried to tell you what is a probability distribution, how do you talk about averages, okay. And the next lecture which I am going to say I will go to the details. Today's were more like preamble and introduction. Tomorrow's or whenever our next meeting is, I will tell you about the equation of state. Already it is very close to what we know about PV is equal to nRT. Can we see that from here? I told you in the beginning that temperature is related to the average kinetic energy. Can we see it from here? How do I get this form at all? What is pressure? Pressure, whose pressure? Particles are hitting the walls of the container and that gives me a force distribution. There is a momentum transfer. This momentum transfer will be related to pressure and I will arrive at this form in the next set of lectures. Thank you for today.